Hi, everyone. Thanks to the organizers for inviting me to this very stimulating event for me. I wanted to actually pick up where Randy left off, and rather than talking about how we remember, think about how we look forward in time, which is the way economists have mostly thought about time in our own modeling, though I think more and more we're recognizing that our memories are also faulty, along with every other belief that we hold. But let me focus now on forward-looking issues. This is the basic model. Let me quickly bring everyone up to speed, probably a model that's familiar to most of you. We economists take the rather bold view that we're constantly representing our entire life in some utility maximization problem. Capital U here is total utility, and total utility is a discounted sum of the utilities that I receive in each, let's say, day of my life, from today, Monday, all the way out to tomorrow, Tuesday, to Wednesday, etc., to the end of my life. And perhaps I'm even thinking about events that will occur after my death. Now, of course, all of those events are weighted, and that's where time will come in critically here. We're going to be weighting those events with a discount factor, D0 for today, D1 for the next day, D2 for the day after that. And our focus, my focus, will be on these weighting functions and what we know about them and what perhaps we don't know about them but are trying to figure out. So we'll focus on those weighting functions, which in economics are the focus of our intertemporal science. The way economists set this up is we just normalize D0, the weighting on today, to be equal to 1. That's just a normalization. There's no content in that. It's really how everything relates to this normalized D0. Well, people seem to care more about what's happening now than what will happen in the future. So generally, we take the approach, empirically driven, that this D function is declining as we go out further in time. D0 greater than D1, greater than D2, etc. We usually assume, though I'm going to challenge this later on, that these are deep preferences, meaning we really do care, we humans really do care more about today than tomorrow than the next day. That's not a mistake, that's not a cognitive error, that's not a perceptual problem. That is a legitimate expression of our preferences. These are our human tastes. And I'll just refer to this again and again as the discount function, and I'll use red coloring to keep reminding you of that object, d of tau, the discount function, where tau is the horizon at which we're discounting. So if tau is 5, we're discounting 5 periods into the future. For our purposes today, those might as well be days. Okay, so let's interpret this object, the discount function, that will be the focus of what I will be discussing. 1 util experienced today is as good as 1 over d of tau utils experienced in tau days. That's what the notation on the previous slide directly means. So why is that, in case it's not already obvious? Well, 1 util we can think of as being derived by discounting with our discount function d of tau, utils that will come in tau periods. So how many utils do I need in tau periods so that once they're discounted, they're worth 1 util today? Well, 1 over d of tau utils received in tau periods. Okay, now here's a discount function. Not necessarily one that you'll find that comforting. This function has a declining weight, declining 1% per day the further out I go in time. So every day we're depleting value by an additional 1%. We'll come back to that particular functional form later, but for now, here's how it looks. Here are days on the horizontal axis, here is value on the vertical axis, and here's that normalization. The weighting function for today, date 0, now is 1, and we're declining 1% a day. Now, there's lots of evidence that humans discount between today and tomorrow far more than 1%. But the problem is if you take 1% and you keep exponentiating it, 1%, 1%, 1%, well, you get to some pretty nasty conclusions like this. This tells me that if I discount 1% a day in this kind of stationary form, well, after a year, a util received in 365 days is only worth 0.026 utils today. And therein lies a kind of paradox that we're going to keep coming back to. So what does that mean? That means that I would need 38.5 utils to be handed to me in a year to make me indifferent between that reward and getting 1 util right now. Now, I'm guessing there's no one in this room who is that impatient that you would say, I need 38.5 in a year in return for 1 util right now. Of course, you might ask, what the hell is a util? But let's not worry too much about that right now. I'm an economist. Pleasures and pains. So we've just laid out the setup. That is the framework that we economists use to think about intertemporal choice. Now, there's lots of variations on a theme, and we could go on for hours if we wanted to get to all the details, but in 25 minutes, let me set that as my introduction. Exponential discounting is our next topic, and that is the function you already saw. If we're going to discount at the same rate each period, in this case days, that is an exponential discount function. Mathematically, we can write it this way: d of tau equals some factor, here 0.99, representing 1% devaluation per period, raised to the tauth power, where tau is the number of days. This is the picture you saw before, but now I'm just reminding you that this implies a constant rate of decline, i.e. constant proportional decline. It's not a constant slope, of course, but it's a 1% decline in the value each period, which produces this bow-shaped curve as the value falls, and hence a proportional decline requires a smaller and smaller absolute decline the further out we get. Now here's that exponential discount function written now with a parameter delta, the so-called discount factor. This says events tau periods in the future are discounted by the discount function delta to the tauth power. Now, that discount function is going to generate something called dynamic consistency, which is kind of nice in theory and perhaps kind of empirically untrue, but at least for now, let's focus on the nice in theory. What does this mean? Today's preferences about future decisions do not change with the passage of time. And that's a kind of conditionally do not change. So here's an example. David Laibson plans to start an exercise regime after I finish teaching my courses this spring, unless I have a legitimate excuse like a broken bone or something. And I'm dynamically consistent if I in fact do start an exercise regime after I finish teaching my courses this spring. Again, conditional on that kind of escape clause. I don't want to, promise to do things that I really don't want to do. I want to promise to do things in the state of nature where it's appropriate. The good news is exponential discounting implies dynamic consistency, one of the reasons economists started there and have been developing that framework over the last century. The bad news is that the evidence overwhelmingly suggests that we in fact do not discount exponentially. In fact, when we look at the discount functions that we measure when we study human behavior, and there are now, I'm guessing 1,000 studies, maybe many more at this point, trying to get at these discount functions, what seems to be the case is that the discount function doesn't decline at a constant rate, the exponential form. Instead, it seems to kind of fall relatively quickly in the short run and then kind of decline at a relatively slow rate. These are sometimes called hyperbolic functions. The particular functional form we focused on in economics is this present bias form that I'll have more to say about in a second. But the key point is it doesn't look exponential in the data. It looks more like these hyperboloids sharply falling and then kind of flattening out a bit thereafter. So the present bias discount function, the one you saw on the previous slide, actually looks like this. It was first developed by Phelps and Pollock to think about intergenerational discounting in the 60s, and I've been applying it to intrapersonal discounting, meaning me today, me tomorrow, me the next day, more recently. It simply says that the discount function isn't delta, delta squared, delta cubed, the exponential form we saw before, but now we're going to take a new parameter, beta, and stick it in front. And this beta is a wedge between all the future periods and today. So beta separates later from now, and this critical beta parameter is going to kind of dominate the show for the next couple slides. Think intuitively about the case beta equals a half, delta equals 1. In that case, my discount function looks like this, very simple. I put full weight on the present, there's my normalization to 1, and then once I get to tomorrow, I've only got half weight. So I'm very present biased. I'm focused on rewards right now. If the rewards come later, well, they're worth less, half less in this example, but then they kind of plateau. So I don't draw a big distinction between, next Friday and next Saturday and next Sunday, but I draw a big distinction between the rewards I'm going to have today, Monday, and the rewards I'm going to have tomorrow, Tuesday. That's the big wedge. Once I get to Tuesday, I kind of think of time as not sharply distinguishing periods. They're kind of all the same to me in this simple special case. Here's an example that I like to use to teach this distinction. Think about exercise, my own struggle. It costs 6. I don't like to exercise. Maybe you like to exercise, in which case you're lucky, but most humans don't like it. It has an upfront cost, but my physician, my family, everyone I know tells me it has delayed benefits. Let's call those 8. Well, will the agent exercise? Today, for example, well, there's an immediate cost of 6. There's a delayed benefit of 8. The delayed benefit's getting multiplied by this compound factor beta times delta. That's the relevant calculation for exercising. Here's the decision to exercise tomorrow from today's perspective, made from today's perspective. Now beta and delta multiply this minus 6, the cost I'll pay for exercising tomorrow. There'll be even more delayed benefits after that, multiplied by an additional delta. There's that exponential discounting coming in, multiplying the 8. Well, let's put parameters on this to see how all this works. Remember, delta we can think of as very close to 1. So let's replace delta with 1. And beta we can think of for this illustrative case as very close to 1/2. Let's replace that with 1/2. And now we have a kind of interesting paradox, because this calculation tells me that David Laibson will not exercise today, Monday, but David Laibson, from today's perspective, plans to exercise tomorrow, Tuesday. I think you can all see where that's going to go. So agents in these models are not dynamically consistent. They plan today to exercise tomorrow, and they will not follow through unless they find some ways to commit themselves. And we can talk about all the ways that we humans do and don't get around to making those commitments. Happy to share the slides, by the way, if anyone wants them. So let's think about why the world in practice looks present biased or hyperbolic rather than the exponential form that we talked about at the beginning. And I'm going to talk about 6 mechanisms that explain why perhaps we're more present biased or hyperbolic than we'd like to be if we were kind of shooting for this dynamically consistent world that I think does not apply. Here are the 6. Well, 6 mechanisms that generate discounting generally, and then we'll talk in particular about why these hyperboloids keep showing up. So there's mortality weighting. Why do I discount the future? Eat, drink, and be merry, for tomorrow you may die. Well, the good news is mortality rates are really low right now in the developed world, so that can't explain 10% discounting over the next week. It can't explain this vast rate of impatience, even for animals, frankly, non-human animals, I should say. We're basically going to be here tomorrow, so a 1% daily discount rate just doesn't make sense. Moreover, mortality discounting would say it's the grandparents who are the vastly impatient people and the 5-year-olds who are incredibly patient. Of course, we know that's ridiculous. Another mechanism is exponential time preferences. We really, really do care more about now than later in this exponential form, and that's a legitimate deep preference. Another mechanism is that we really are present biased, that we really do value the present more than the future, and that's a legitimate preference that we hold that has to be given some normative merit. But I want to focus more on the items at the bottom of the slide, which are kind of other psychological mechanisms that may explain a lot of this discounting behavior, not so much as the result of these classical preference-based interpretations, but through other channels, often a cognitive channel. So I want to talk about multiple cognitive systems interacting. I want to talk about heuristics and psychometric models. I want to talk about myopia very quickly. Okay, now, in reviewing those 3 mechanisms at the bottom of the slide, the first mechanism is this idea that we are a composite of brain systems. And those systems obviously aren't kind of cleanly divided. There isn't some sharp separation between system 1 and system 2 and system 17. But for the purposes of this conversation, very crudely, let me imagine that there are these multiple systems. And in every case on the slide, I'm kind of referring to a literature where the first system is kind of more deliberative, more analytic, and the second system is more emotional and affective. Plato, talking about Socrates, said it a long time ago in 370 BC. And you can excuse him for his slightly outmoded notions of nobility. I think he had the psychology perhaps at least partly right. First, the charioteer of the human soul drives a pair. And secondly, one of the horses is noble and of noble breed, and the other quite the opposite in breed and character. Therefore, in our case, the driving, meaning us running our own lives, is necessarily difficult and troublesome as we try to control these competing forces. Adam Smith, known as the father of economics, actually had a lot to say about these competing internal interests. Interests, which we can think of as the more deliberative side, versus passions leading us to our ruin. Freud had a three-pronged system. I'm not sure we're even allowed to mention Freud anymore, but he didn't get everything wrong. There's controlled versus automatic. There's cold versus hot. There's system 2 versus system 1, very popular these days. There's deliberative versus impulsive. There's conscious versus unconscious. There's effortful versus effortless. There's the planner versus the doer in the econ literature. There's patient versus myopic. There's abstract versus visceral. And in terms of the neuroanatomy, there's the PFC and the parietal cortex versus the dopamine reward system, and I'll talk more about that in a moment. All of these discussions imagine these kind of two fundamental forces: an analytic system that's effortful, slow, conscious, reflective, and forward-looking, and an affective system that's faster, unconscious, reflexive, and relatively myopic. Not completely myopic, but more prone to be focused on the present. So I want to contrast the neuroanatomical understanding of these competing forces. The frontal cortex and the parietal cortex, using neuroimaging, seem to be more about self-regulation, more about these forward-looking, goal-seeking activities. And the dopamine reward system, sometimes called the limbic system, depending upon how old you are, seems to be more oriented towards immediacy and approaching things or making decisions that are focused on immediate rewards and costs or relatively short-run decision-making. There's integration. The work of Antonio Rangel has emphasized that the medial prefrontal cortex or the ventromedial prefrontal cortex or the medial orbital frontal cortex, regions that are very hard to distinguish neuroanatomically, seem to be where these signals join up. And there's a kind of growing understanding of these kind of differential value systems producing some integrated decision-making, which of course represents the final behavior that we see. Let me map this back to our discussion of present bias in a very crude and just illustrative way at first, and then we'll use a little modeling in a second. Let's think about the frontal parietal system as being relatively patient. Of course, not completely patient as I have it on the slide, but just relatively patient. So the PFC, let's think, puts weight 1 on all rewards, whether they come now, today, Monday, or tomorrow, Tuesday, or Wednesday, etc. Whereas this dopamine reward system is relatively impatient. In this case, I've made it rather stark. The dopamine reward system only cares about the ice cream I'll get today and isn't at all concerned about the ice cream I'll get on Tuesday, Wednesday, or Thursday. Imagine for the moment that we are just a combination, additive of these two systems. Let's add them together with equal weights. A crude discussion for now. If I represented you as the sum of these two systems, what would your weights be? Well, 2, 1, 1, 1, out to infinity. Let's just norm that because it doesn't really matter where we start. If we normalize that and make the first period 1, we have 1, 1/2, 1/2, 1/2, which is another kind of illustration of this present bias here coming from two systems with different preferences co-joining to drive your decision making. Now we can do it a little more formally. Using the notation that I introduced a few slides ago. If we think about total utility as being the sum of current utils plus beta discounted future utils, with exponential discounting separating each of those future utility events, well, I can transform that without changing any of your preferences by multiplying both the left and right-hand side by a multiplicative constant, 1 over beta. So I have 1 over beta capital U, and then I have this beta here vanishing and little u taking on a 1 over beta multiplicative term. I can then partial out ut from this expression over here, and I now have decomposed your total utility into immediate utils, which I can think of as the dopamine reward system, and all other utils weighted exponentially, which I can think of as the prefrontal cortex or some cortical, more analytic representation of my life. And so here I am, a combination in this very crude example of preferences driven by the dopamine reward system, relatively impatient preferences, and preferences driven by the frontal parietal cortex, relatively patient, let's say, in this case, fully exponential discounting. That's one mechanism. Here's another. I've talked so far about interacting systems. Well, here's just a kind of heuristic psychometric interpretation for all of these hyperboloids that show up in our discount functions. Imagine that you're engaged in a lot of proportional reasoning, or your perception, your psychometrics are proportional psychometrics. Here's an example. Suppose you're choosing between an early reward and a delayed reward, and you devalue the delayed reward based on how much longer it makes you wait as a proportion of the average waiting time, a kind of standard ratio reasoning, which doesn't have a lot of economic logic, but is very appealing to our kind of intuitive brains, our intuitive minds. If that's the way you think about the world, think about differences in delays, norm that by average waiting time, you're going to end up with those hyperboloids showing up everywhere in your discounting patterns. Now, in this formulation, doubling the wait time to 2 weeks from 1 week is as value reducing as doubling the wait time to 2 years from 1 year. And hence, you won't be an exponential discounter, you'll be a kind of hyperbolic or present bias discounter in this proportional reasoning world. Another mechanism that I think is legitimately driving a lot of the data that we see in the human experiments, and probably too in the animal model. Finally, a third mechanism I want to touch on in the time remaining, myopia. Lately, I've been thinking with Xavier Gebex, and it turns out we are following in the footsteps of Mike Woodford, our very, very brilliant friend who happens to be here today, in thinking about how myopia and imperfect learning may be driving a lot of the behavior that we see in this intertemporal choice data. Here's an example to kind of motivate the conversation. Imagine a driver who sees an upcoming pothole and estimates that it's very small, maybe just a dip in the road, she thinks. But a few seconds later, as she approaches the pothole, she realizes it's car size. And she's got to get out of the way quickly or she's going to damage her car, or worse, she swerves, she crashes. Is that because she was so impatient that she didn't care about what was going to happen 4 seconds later, and that's why she was engaged in this passive, inactive driving? No. This was imperfect information, not impatience, that led her to fail to slow down when she first noticed the irregularity in the road. So in this case, she was misestimating future consequences, not reacting in an impatient manner to future consequences. So one can reinterpret her behavior as a cognitive mistake, not as an example of highly impatient behavior. Let me formalize that in the next few slides. So imagine you're sitting at time 0 and you're offered an opportunity to receive either early utils at period t or late utils at period t plus tau. Imagine that you simulate the world, and you simulate the world with noise. You're not a perfect forecaster. You do everything in life with a little bit of noise. So when you simulate the utils at day t, you simulate them with noise epsilon t. When you simulate the utils at period t plus tau, you simulate them with noise epsilon t plus tau. Of course we do. Well, imagine as well that the forecasting noise is proportional to the time horizon. In particular, imagine that the variance of your forecasting noise increases linearly in the horizon of the forecast. The further away you forecast, the more the noise. Write down the crude assumption that it's a linear function. Well, in that case, you will end up as a decision maker who's a fully Bayesian, fully rational decision maker who is perfectly patient, and yet when you get signals about the future, you're going to discount them because of the noise and because you are trying to engage in a sophisticated inference about whether that signal you got is a legitimate signal about the future or just a kind of misperception about what's coming. And because you've got priors and because you're trying to do as well as you can in light of those priors, you're going to downweight all those signals because there's noise in those signals. Your expectation of the value of those utils will be discounted optimally by a discount function d of tau, which takes precisely this hyperboloid form. The discount function that you'll have is 1 over 1 plus alpha tau, where alpha is the per period simulation variance, and divided by the background variance of utility events in your environment. So you'll be a hyperbolic discounter for perfectly rational Bayesian reasons. The intuition here is the following. Even rational agents have a hard time imagining and forecasting the future. Their forecasts are noisy. Consequently, these Bayesian, these rational agents, tend to downweight future events that are real or legitimate, like that pothole, because they don't know whether the little thing they're seeing on the horizon is a mile-deep pothole or just a little bump in the road. And so, of course, they don't respond to it in advance. We know, sitting in a helicopter above them, it's a giant pothole. Swerve early. But they don't know that. So when they don't respond, it's not impatience, it's just imperfect forecasting. Let me summarize in the 30 seconds I have remaining, or maybe less than 30 seconds remaining. Agents strongly discount future events. I think now there's overwhelming evidence for that in the literature, both animal and human models. Discounting tends not to follow an exponential form. We don't have a consensus view in economics, and I think as I talk with great interest to my colleagues in other fields, I don't think there's a consensus view anywhere on why people are doing so much discounting and why it's not exponential in functional form. I've discussed 3 mechanisms today that I think all jointly contribute to these non-exponential discounting forms. And they are, to quickly review, A, multiple interacting systems, some of which are more patient, some of which are less patient, and which jointly produce behavior that appears to be relatively hyperbolic in its preferences and its discounting. Heuristics of perception and proportionality that lead us to use time ratios rather than exponential discounting to intuit how we should be evaluating the future. And then this myopic mechanism whereby, because we can't forecast the future correctly, and because there's lots of noise in all of our forecasts, we pretty rationally say, hey, I'm not going to over-respond to events that I really can't predict. And if I'm not responding to events I can't predict, I'm going to look relatively impatient because I am responding to the things I can predict happening right now and being relatively prone to under-respond to events that are coming in a year or a decade or even a half lifetime away. Thank you very much.